March 15, 1987, Gary, Indiana. The plant manager stood before the 28-ton Cincinnati planer that had occupied the same spot on the factory floor since 1912, calculator in hand, running numbers that all pointed to one conclusion. This machine had to go. 75 years of continuous service meant nothing against modern efficiency metrics. The planer consumed 18 feet of prime floor space that could house 3 CNC mills. Its single-point cutting tool crept across workpieces at speeds that seemed glacial compared to modern multi-axis machining centers spinning at thousands of RPM. Most damning, the nearest machinist who actually knew how to operate the ancient tool was approaching retirement age, and no apprentice wanted to learn skills they assumed were obsolete. The equipment liquidation consultant's appraisal valued the machine at $1,200 as scrap metal, perhaps $3,000 if a museum or nostalgic collector could be found. For a company bleeding money in an industry crushed by foreign competition, the decision seemed obvious. Clear the floor space, sell the antique, install modern CNC equipment that promised faster cycle times and lower labor costs. This same scene was playing out across American manufacturing districts throughout the 1980s. In Cleveland, a 1910 Bickford planer rolled onto a flatbed truck destined for the torch. Milwaukee shops auctioned off gray planers that had flattened armor plate during 2 world wars. Detroit factories, desperate to compete with Japanese automotive suppliers, scrapped the massive planers that had machined engine blocks and transmission cases for half a century. The logic appeared irrefutable to MBA-educated managers armed with spreadsheets and efficiency consultants. Planers represented the old way. Single-purpose machines requiring skilled operators, producing one surface at a time, consuming enormous space relative to their output. CNC mills embodied the new paradigm. Versatile, fast, computer-controlled equipment that could machine complex parts with minimal labor while occupying a fraction of the floor space. What none of these managers understood was the physics problem they were about to create. The planer's apparent limitations, its massive weight, rigid construction, methodical cutting action, and specialized purpose, weren't obsolete engineering from a bygone era. They were solutions to fundamental mechanical challenges that CNC technology hadn't actually replaced, only obscured through clever marketing and the assumption that faster must mean better. The 1912 Cincinnati planer that faced the scrapyard that March morning in Gary represented something the modern manufacturing world had forgotten. Sometimes, the answer to how do you machine a perfectly flat surface on a 8,000-pound steel casting isn't use a more sophisticated computer, but rather use a machine built when engineers understood that some jobs require mass, rigidity, and mechanical advantage that no amount of spindle speed can substitute. Before the decade ended, the shops that had kept their planers would discover they possessed the only tools capable of certain critical operations. The shops that had scrapped them would learn why some old technology doesn't become obsolete. It just waits for the moment when modern alternatives reveal their limitations. The Cincinnati Planer Company's factory floor in 1912 produced machines that embodied a completely different manufacturing philosophy than what would emerge a century later. Master pattern makers spent weeks creating the wooden forms for casting the planer's bed, a single, continuous piece of cast iron weighing up to 40 tons for the largest models. The casting alone required metallurgical precision that modern engineers struggle to replicate, cooling rates calculated to prevent internal stresses, iron compositions that balanced strength with dampening properties, ribbing patterns that distributed forces without adding unnecessary weight. Once cast and rough machined, each planer bed underwent a seasoning process that seems absurd by contemporary standards. The casting sat outdoors through complete seasonal cycles, summer heat causing expansion, winter cold inducing contraction, allowing the iron's molecular structure to stabilize naturally. Only after this year-long wait would final machining begin, using other planers to create the precision ground ways that would guide the machine's table for the next century of operation. The mechanical elegance of these machines reflected engineering principles that predated computer optimization but achieved results modern software struggles to match. The cutting head moved on a ram supported by bearing surfaces measured in square feet, not square inches, This massive contact area distributed forces so effectively that cutting tools could remove material from hardened steel without deflection, chatter, or loss of dimensional accuracy. Feed mechanisms used nothing more sophisticated than ratchet wheels and pawls, yet achieved repeatability within thousandths of an inch across cutting strokes measuring 12 feet or more. The table's reciprocating motion relied on gear trains with teeth hand-scraped to ensure perfect mesh, a process requiring weeks of skilled labor per machine, but resulting in mechanisms that could operate continuously for decades without appreciable wear. By the 1920s, planners had become indispensable for manufacturing everything that defined industrial civilization. Locomotive frames, ship engine beds, turbine housings, press components, and structural elements all required the dead flat surfaces that only planers could reliably produce. The Bethlehem Steel Works operated 37 planers simultaneously, their synchronized cutting strokes creating the rhythmic metallic chorus that characterized heavy manufacturing districts. Tool steel manufacturers developed specific alloy grades optimized for planer cutting tools, high-speed steels that could maintain their edge. Through interrupted cuts spanning minutes at a time, cutting fluid formulations evolved to handle the unique thermal conditions of planer operations, sustained cuts that generated heat differently than the rapid, repeated engagement of milling operations. The machine's utility extended beyond simple surface generation. Skilled operators could produce compound angles, stepped surfaces, and geometric features with nothing more than careful setup and the planer's basic motions. A 1928 machining handbook documented 47 distinct operations possible on a standard planer, each requiring understanding of mechanical principles rather than computer programming. The same characteristics that made planers essential, their massive construction, specialized purpose, and reliance on operator skill, would later make them targets for elimination when manufacturing philosophy shifted from building machines that lasted generations to maximizing quarterly returns on equipment investments. The Milwaukee Milling Machine exhibitions of 1947 presented a vision that terrified planer manufacturers. Horizontal mills with power feeds and multi-tooth cutters that could machine flat surfaces 5 times faster than planers while occupying half the floor space. The Kearney and Trecker demonstrations showed a 500-pound casting machined completely in 45 minutes, work that would have taken 3 hours on a planer. Brown and Sharp's technical presentations emphasized versatility over specialization. A single milling machine could handle face milling, end milling, gear cutting, and complex contour work. Planers could only plane. The cost comparison seemed devastating. A modern mill at $18,000 versus floor space and overhead for maintaining a planer installation worth perhaps $30,000 in replacement value. Forward-thinking shops began reorganizing around milling operations. The Cincinnati Milling Machine Company's order books filled with contracts from manufacturers who saw the future in multi-purpose machine tools. Trade journals published efficiency studies showing how milling operations reduced labor hours per part while improving surface finish quality measurements. Yet this first wave of planer eliminations revealed a pattern that managers initially dismissed as anomaly. The Gardner Machine Company of Beloit, Wisconsin scrapped their 1915 Niles planer in 1952, redirecting all flat surface work to their new Cincinnati mill. Within 6 months, they faced a contract for railroad car truck frames, castings weighing 200 pounds each, requiring flat surfaces accurate to within 0.05 inches across 8-foot spans. The mill's table couldn't physically support the casting's weight without deflection. Attempts to machine the surface produced geometry errors exceeding specification by factors of 3. The spindle head's bearings, designed for interrupted cuts on smaller work, vibrated when taking continuous cuts through the casting's hard spots. After ruining 2 castings and breaking 3 cutting tools, Gardner subcontracted the work to a competitor who still operated a planer and watched their profit margin evaporate in the process. Similar stories emerged from shops across the manufacturing belt. The Farrell Birmingham Company discovered their new mills couldn't handle the 14-foot bed plates for hydraulic presses. A Detroit automotive supplier found that cylinder head surfaces machined on mills developed warpage problems that planned surfaces never exhibited. Pattern shops learned that mill-cut aluminum tooling plates required additional hand scraping to achieve the precision that planers produced directly. The technical explanations were straightforward to engineers who understood structural mechanics, but counterintuitive to managers focused on cycle times. Milling machines generated superior surface finish through high-speed cutting action, but their relatively light construction and cantilevered cutting forces made them vulnerable to deflection on heavy workpieces. Planners worked slowly precisely because their cutting tools engaged material continuously across the entire stroke, a mechanical action that actually improved accuracy on large castings by maintaining constant cutting forces. By 1960, a peculiar market had developed. Shops were buying new mills for general machining while quietly keeping their old planers for the jobs that exposed milling's limitations. The machine's survival seemed assured through specialized utility rather than general superiority. Then came CNC, and with it a conviction that computer control could overcome any physical limitation. The 1983 International Machine Tool Show in Chicago featured Mazak's showcase demonstration, a 5-axis CNC machining center producing a turbine blade from solid billet, cutting speeds that made the metal glow orange, tool changes executed in 2.8 seconds, dimensional accuracy to 0.001 inches. The future of manufacturing seemed definitively settled. Computer numerical control had arrived, and it promised to make every previous machine tool technology obsolete. Management consultants descended on American factories with compelling presentations. The typical pitch quantified everything. CNC mills reduced setup time by 73%, decreased scrap rates by 68%, and cut labor costs by 81% compared to manual machines. Payback periods of 18 months seemed conservative. The machines could run lights out, producing parts overnight without operators. A single CNC cell could replace 4 conventional machines and their operators. What the presentations never mentioned was maximum table load capacity. The specifications existed in technical manuals, typically 2,200 pounds for a standard machining center, perhaps 6,600 pounds for heavy-duty industrial models. But salesmen emphasized speed, precision, and automation benefits rather than weight limitations. The Randall Corporation of Rockford, Illinois, typified the wholesale conversion to CNC. Between 1984 and 1987, they invested $4.3 million in new machining centers, gutting their conventional machine shop to create temperature-controlled CNC cells. The 1916 gray planer that occupied 240 square feet of prime floor space became a symbol of the old way: massive, slow, manually operated, and economically indefensible. The plant manager's analysis proved mathematically irrefutable. The planer's maximum cutting speed of 60 feet per minute seemed pathetic compared to CNC mills running at 800 inches per minute with multiple simultaneously engaged cutting edges. Annual maintenance costs for the planer's outdated drive systems exceeded $7,000. Insurance costs penalized the shop for operating equipment lacking modern safety guards. Most damningly, only one machinist on the floor, 62-year-old Harold Simmons, possessed the knowledge to set up and operate the machine properly. Randall listed the planer with industrial equipment brokers at $8,500, then $4,000, finally accepting $2,200 from a machinery dealer who specialized in exports to developing countries. The removal process took 2 days with a crane and rigging specialists. The freed floor space allowed installation of another CNC vertical machining center and a coordinate measuring machine for quality control. For 18 months, Randall's efficiency metrics validated every assumption. Cycle times dropped, labor costs fell, and the CNC cells produced parts with remarkable consistency. The company won new contracts from customers impressed by their modern capabilities and ISO 9001 certification. Then the Delaney Industries contract arrived: 30 9,400-pound welded steel bases for hydraulic test stands, each requiring 6 flat surfaces perpendicular within 0.003 inches across dimensions exceeding 9 feet. The engineering department spent 3 weeks trying to develop a CNC machining strategy that would work. Every simulation predicted the same problems: table deflection under load, cutting tool chatter from interrupted cuts in welded structures, and thermal expansion issues from sustained machining of such large masses. Randall would need to subcontract the work or rent time on someone else's planer. They had scrapped the only machine capable of handling the job, The fundamental problem emerged from physics principles that no computer program could circumvent: cutting forces, structural rigidity, and thermal mass relationships that favored machines built when engineers designed for mechanical advantage rather than electronic sophistication. A CNC vertical machining center applies cutting forces through a spindle mounted on a column, creating a cantilevered structure where every inch of extension from the column multiplies deflection at the tool tip. The mathematics are unforgiving. A 500-pound cutting force applied 30 inches from the column face on a typical machining center produces measurable deflection exceeding acceptable tolerances for precision flat surface generation. The deflection increases exponentially with workpiece weight as the table structure deforms under load. Modern machine tool manufacturers address this through various engineering solutions: heavier bases, wider ways, larger ball screws, and sophisticated vibration dampening systems. These improvements worked remarkably well for workpieces within the machine's design envelope, typically components under 3,000 pounds. Beyond that threshold, physics imposed limitations that no amount of structural engineering could overcome without essentially recreating planar design principles. The 1912 planer approached the same problem from opposite mechanical principles. Its cutting tool moved horizontally across a workpiece secured to a table that moved perpendicular to the cut on ways measuring 18 inches wide with bearing surfaces totaling 12 square feet. The bed's 32-ton mass provided thermal stability and vibration dampening that computer-controlled systems couldn't replicate. Cutting forces directed through the ram into bearings distributed across massive surfaces created deflection so minimal that measurements required precision instruments to detect. The machine's slow operating speed, apparent weakness to efficiency consultants, actually enhanced accuracy for large workpiece machining. Each cutting stroke engaged material continuously for 30 to 90 seconds, allowing the cutting tool, workpiece, and machine structure to reach thermal equilibrium. CNC mills achieved faster cycle times through rapid engagement and disengagement of multiple cutting edges, but this interrupted cutting action generated thermal pulses that caused dimensional instability on massive castings and weldments. The practical implications became obvious when machine shops received jobs requiring flat surfaces on components weighing between 4,000 and 20,000 pounds, pump housings for chemical plants, base plates for production presses, structural components for mining equipment, and frames for heavy industrial machinery. CNC machining centers simply couldn't handle the physical requirements regardless of their sophistication. The workpiece weight alone exceeded table load capacities, forcing operations to machine components in multiple setups that destroyed the geometric relationships that single setup planing naturally preserved. When shops attempted to machine such components anyway, using heavy-duty machining centers rated for higher loads, the results consistently failed to meet specifications. Table deflection produced convex or concave surfaces rather than true planes. Thermal expansion from sustained cutting created dimensional errors that appeared only after the workpiece cooled to room temperature. The shops that had scrapped their planers discovered they had eliminated the only tool capable of certain operations that modern industry still required. The machines they had dismissed as obsolete artifacts actually represented solutions to problems that CNC technology had never genuinely solved, only avoided by staying within weight and size limitations that traditional planers had routinely exceeded. By 1991, a peculiar market phenomenon had emerged in industrial equipment circles. Vintage planers from the 1910s and 1920s were appreciating in value while most other pre-CNC machine tools sold for scrap prices. The reversal mystified equipment dealers accustomed to depreciation curves where older meant less valuable. The Gorton Machine Works of Racine, Wisconsin discovered their presumed mistake had become strategic advantage. They had kept their 1914 Cincinnati planer primarily through inertia rather than foresight. Nobody wanted to pay for removal of the 26-ton machine, and its location against a structural wall made extraction difficult. When aerospace contractors began seeking shops capable of machining large aluminum bulkheads for commercial aircraft, Gorton found themselves with the only equipment in a 200-mile radius capable of handling the 12-foot components. The contracts arrived from unexpected sources: Defense contractors needed bases for radar equipment machined from solid aluminum plates weighing 8,000 pounds. Energy companies required precisely flat mounting surfaces on turbine housings that CNC shops couldn't accommodate. Heavy equipment manufacturers discovered that their modern machining centers couldn't produce the geometric accuracy their 1960s planers had routinely delivered on large press components. The machine's rehabilitation required rediscovering knowledge that had nearly disappeared. Gorton's senior machinist, Carl Hendricks, had learned planer operation as an apprentice in 1967 before the machines fell from favor. He still understood the setup procedures, indicating the work table's movement parallel to the ways within 0.001 inches across the full stroke, setting cutting tool angles to minimize chatter, calculating feed rates based on material properties rather than computer-optimized parameters. Younger machinists accustomed to G-code programming found the planer's purely mechanical controls challenging initially, then liberating. The machine provided immediate tactile feedback about cutting conditions. When the cutting tool encountered hard spots in castings, operators felt the load change through the machine's structure and could adjust feed rates instantly. CNC mills required sensor packages and sophisticated monitoring software to detect conditions that planer operators perceived through experience. The parts supply challenge proved solvable through unexpected means. The planer's drive systems used components, V-belts, bearing assemblies, gear sets, based on standard dimensions that industrial suppliers still maintain for other applications. Unlike CNC machines, requiring proprietary controllers and specialized servo motors available only from original manufacturers, the planer's mechanical simplicity meant that competent machine shops could fabricate replacement parts from drawings or actual worn components. The work itself demonstrated why planers remained essential. A mining equipment manufacturer contracted Gorton to machine bed plates for rock crushers, welded steel fabrications weighing 13,000 pounds, requiring 4 flat surfaces perpendicular within 0.005 inches. The planer completed the work in 2 setups over 3 days, producing surfaces that met specification without secondary operations. 3 CNC shops had rejected the contract as impossible with available equipment. By 1995, Gorton's planer generated 22% of the company's revenue while occupying just 6% of their floor space. The machine they had almost scrapped had become their most profitable asset. Shops across the manufacturing belt were discovering similar redemption stories, realizing that some old technology doesn't become obsolete. It just waits for modern alternatives to reveal their limitations. The paradox of 21st century manufacturing lies in a machine tool built during Woodrow Wilson's presidency, remaining essential while equipment purchased during the Obama administration heads toward obsolescence. Yet this reality defines current heavy industrial machining. Vintage planers from 1910 to 1930 command premium prices while representing capabilities that modern machine tools fundamentally cannot replicate. The technical explanation centers on limitations that aren't temporary engineering challenges awaiting better solutions, but rather fundamental physics constraints that increasingly sophisticated control systems cannot overcome. Modern 5-axis CNC machining centers costing $800,000 can produce geometric complexity that 1912 planers never attempted. Yet they cannot machine a true flat surface on a 10,000-pound casting because structural mechanics impose inviolable limits on machines designed for versatility rather than specific rigorous operations. Contemporary shops requiring large flat surface generation face stark choices. They can subcontract work to the diminishing number of facilities maintaining vintage planers, accepting lead times and logistics costs. They can attempt workarounds using large CNC gantry mills designed for aerospace applications, accepting geometric compromises and substantial hourly rates. Or they can acquire their own vintage planer if floor space and operational knowledge permit. The acquisition market reflects this reality through pricing that reverses normal equipment depreciation. A 1918 Niles planer in operational condition commands $35,000 to $65,000 despite being a century old. Comparable-sized manual mills from the 1960s sell for under $5,000. The valuation differential measures capability gaps that modern machine tools haven't closed. Industrial archaeology reveals similar patterns across manufacturing technologies. The shops that maintained seemingly obsolete capabilities discovered competitive advantages when niche applications justified specialized equipment. Pattern makers kept their ancient shapers for producing curved surfaces that CNC routers couldn't match economically. Tool and die shops preserved manual surface grinders for operations requiring the tactile feedback that automated grinding systems eliminate. The broader lesson extends beyond planers to fundamental questions about technological progress. The assumption that newer automatically means superior ignores situations where older technologies solved problems so effectively that replacements represent lateral moves, trading different advantages rather than clear improvements. CNC machining centers excel at geometric complexity, rapid tool changes, and lights-out operation. Planers excel at massive workpiece capacity, structural rigidity, and sustained heavy cutting. The 1912 planer that shops tried to scrap in 1987 operates today in a Wisconsin manufacturing facility, producing components for wind turbine nacelles, technology its builders never imagined. The machine runs second shift, with a 34-year-old operator who learned planer operation through YouTube videos and consultation with retired machinists. The combination of century-old iron construction and modern metallurgy and cutting tools produces results that justify maintaining equipment predating the First World War. The ultimate vindication lies not in nostalgia for old machinery, but in recognition that some engineering solutions achieve fundamental efficiency through mechanical principles rather than electronic sophistication. The planers that survived their near extinction proved that sometimes the obsolete technology isn't the one lacking computer controls, it's the modern equipment that cannot accomplish what the old machines routinely delivered when engineers designed for mechanical advantage rather than marketing trends.